And then all right, attendance is open if y'all want to go ahead and check in. It's open. Don't forget to go ahead and check in. Bless you. All right, so y'all see that we are in the path of a tropical storm there. So we shall see what happens between now and then, but fingers crossed, right? So tomorrow, what is due tomorrow? Your homework. So I know it's a Wednesday, you're not used to this, you're used to having like the whole weekend and that kind of thing. So I'm telling you, you need to go work on your homework tonight, okay? There are bonus points built into it, just like I do every other one since whatever chapter that was. Y'all liked it so much, so I'm okay with that. But you need to get started on it, okay? Do not leave it to go undone, because that homework grade can boost your grade up, okay? All right, we're gonna finish chapter 8 today, which means we're starting chapter 9 next Tuesday. No, Thursday, we're starting chapter 9. Then we'll finish chapter 9 next Tuesday, and then it will be a exam the following Thursday, okay? So we got a lot coming up in the next short while. So make sure you're ready to go. So if you haven't already, go ahead and click in on attendance. Y'all ready for the joke of the day? Yeah. All right. What do you call a fake pasta? An impasta. I had never heard that one before. Apparently, that's a good one. My son didn't even laugh, but I was at the table giggling. So an impasta. But that was funny. All right. Okay, so we're going to start off with a couple of clicker questions. Y'all ready for this? All right, so that was last week's last question. We currently have 74. I'm about to close attendance, so please, please, please do your attendance. Okay, all right, so we have 74. Here's our first iClicker question. Which of these is a colloid? Which of these is a colloid? Oh, I need my chat on too. A minute and a half. Ten seconds. Okay, so what did y'all say? Okay, what's A? A is ampicillin, a liquid that must be shaken before use. This is something that settles. So what do we call something that settles out of solution? What do we call that? A suspension. So A is a suspension. How about Pedialyte, a clear liquid? This one's a solution, right? Because solutions are clear, suspensions will settle. So a fruit and yogurt smoothie, a chunky, thick, turbid liquid. What do we think? If in order to be a colloid, you have to have small particle size. If you can actually see the chunks, it can't be a colloid. So a colloid is something that is cloudy, but won't settle, right? If you have a big chunk of, I don't know, pineapple, right? It's too big in order to be a colloid. What's the definition of a colloid? Something that is cloudy, but the particles are small enough that they're not going to settle. So which one of these three that we have left is a colloid? Lemonade is a colloid. C-O-L-L-O-I-D, a colloid, right? So what does that make C? A fruit and yogurt smoothie, a chunky, thick liquid. If C is not a colloid, what is it? It's a suspension. It's a suspension. Unless you freeze it, eventually it's going to settle. It will. Okay, vinegar, a clear liquid, what is that? This one is a solution. That one is a solution. Y'all really wanted to say that it was the smoothie, but the problem with that is that it's chunky. It's too big. Remember, you've got to have small particle size. Okay, I'm going to leave that one ungraded, but we need small size. Okay. All right. Let's try a new one. Let me see if I can get this in a position where you can see everything. Okay. It's just too much on the screen. Select the correct products for the chemical equation for hydration of Na3PO4. My suggestion is on a sheet of paper in front of you. Do it. Don't look at the answer choices. Do it. I'll give you 2 minutes. 2 minutes. Get a sheet of paper and a pencil and mix it with water and see what happens. Remember, you have till 2 minutes. Oh, 10 seconds. I'll give y'all till 2:05. 10 seconds. Okay, y'all, click in something. Okay. All right, so what happens when you add this substance to water? This is a solid. What does this solid do? It disassociates into 2 different ions. We have a sodium ion, and that ion is going to be aqueous. And we have a polyatomic ion. PO4 is a polyatomic. Okay, so this is PO4. But what do we need? What are we missing here? We're missing 2 things. Charges, number 1. So what is the charge of sodium? +1. What's the charge on PO4? Now you could go look in your polyatomic ion table, or I could just look here and I could see it was a 3, so it's going to be a -3 because this is a 1 and that's a +1. So I know PO4 is a -3 or 3-, doesn't matter to me which way you do it. Okay, am I done? No, what am I missing? I need to balance it. How do I balance this equation? I just need a 3 in front of the Na. Now I have 3 atoms of Na, and I have 1 P and 4 oxygen, right? Okay, so what answer choice should have been correct? Should have been B. It should have been B. Questions on that one? Good. Okay. Don't forget to, what was the other most common? C. Yeah, don't forget to balance. That's the other thing. Don't forget to balance. Okay. All right. Let's try another one. Okay. See if I can move this up. All right. We have a common anesthetic that comes in IV form as a 2.5 gram per liter solution. What is the concentration of this solution in milligrams per deciliter? Okay, I'm going to ask you something before I let you go on this. What's a deciliter? In 1 liter, how many deciliters do we have? Look in your book in the back, or on the, you know, the sheet of lots of things I give you. No, in 1 liter, how many deciliters? 10. In 1 liter, I have 10 deciliters. In 1 liter, I have how many milliliters? 1,000. Okay, now I'm going to give you a minute and a half. I said 1.5 minutes, but I'll give you till 2 minutes. Click in by 2 minutes. So that means you have about 10 seconds left. Okay, so what did you have to do? Dimensional analysis, right? This one's not so bad as long as you know what your conversions are. So I want to go to, what's my goal? Milligrams per deciliter. So let's do grams first. In 1 gram, there are how many milligrams? 1,000. Come on, y'all, wake up. Y'all got this. All right, so grams cancels. I'm in milligrams per liter. Is that what I need to be? Nope. So what do I need to do? I need to convert from liters to deciliters. So I'm going to put liters on top. My liters cancel. In 1 liter, I have how many deciliters? 10. Okay, so I'm left with milligrams per deciliter. And what you can do is you can just cancel zeros and then just move your decimal place twice. So what do you get? So you should get 250 milligrams per deciliter. Good, good. Okay, so keep track of those zeros. All right, one more. All right, now, percent by mass. Oh, you know what, I wrote this. Y'all don't have an F option, do you? Do you have an F option? No, you don't. Okay, well, it's not F. It's not F. All right. Oh, y'all, I mess up on some things. All right. What mass of sodium chloride, NaCl, in grams is present in 5 liters of a 0.9% sodium chloride solution used for IV therapy? I'm telling you to go find your formula. What's your formula? Somebody tell me. Our percent, this one is a grams, so that is a mass by volume, right, is equal to what? The part over the whole, which is the solution. So SOLU, solution, right, times 100. Okay, so I'll give y'all 2 minutes. That's not F. Okay, 10 seconds. So when you plug this in, right, you're given the percent. So that's 0.9% NaCl. Cl. What's the part? The part is the grams, like grams of NaCl. That's our unknown, right? We don't know what that is. What's our solution? 0.5 liters. But what did you have to know? And you could get this off of that equation sheet. What do you know about mass per volume percent? It's always given in what? Grams per milliliter of solution. Y'all, print out that sheet that I give you, bring it to class, have it next to you when you do your homework, like have it with you at all times. It's really great. So if I have 0.5 liters, whoa, if I have 0.5 liters, how many milliliters is that? 0.5, that's an L, not a 2. 0.5 liters is 500 milliliters. Okay, so that's 500 milliliters times 100. Now all you have to do is solve for your unknown. So how do I do that? Multiply this times 500, so 0.9 times 500, and then we need to divide by 100 to get your grams of NaCl. So what do you get? Cancel your zeros. 5 times 0.9, 4.5. Yeah, what'd y'all get? B is correct. B is correct. Okay, the only thing that is a little bit tricky is to know your units, but do you have to memorize that? Y'all, I don't want you memorizing information that you can get off of the table, off of the, I don't know what I call that, your equation sheets and then periodic table, right? So use them, okay? Please, please, please use them. All right, so let's switch over and go do some problems. All right. See if I can. All right. What is the concentration? Oh, I did this. I did this in the video. I did this in the extra video because I made a mistake on it, and so I made an extra little thing to fix it. But let's do it real quick. What's the concentration in millimoles per liter of a Ca2 plus solution that is 2.50 milli equivalents per liter? We want to get to millimoles per liter. So I know in 1 milli equivalent of Ca2 plus, I'm sorry, we have 2 milli equivalents in 1 millimole of Ca2 plus. How do I know that? That's a 2. How do I know that? What? The charge. All it is however many moles you have, how much charge you have is that equivalent. So you're going to keep your milli and just say, okay, if I have this many moles of calcium, I'm going to have double the number of charges. And so what do we get? 2.5 divided by 2, 1.25, right? Where am I? Millimoles per liter of Ca2 plus. Okay. Let's do the next one. What's the concentration in milli equivalents per liter of an Mg2 plus solution that is 100 millimoles per liter? I'm trying to get to milli equivalents per liter, so I don't have to mess with my liter. But I know there's a relationship between millimoles and milli equivalents. How many milli equivalents do I have? Two milli equivalents for every 1 mole. So what do I get? 200 milli equivalents per liter of Mg2 plus. Okay. All right. What is the molarity of 250 milliliters of solution containing 4.20 moles of ZnCl2? What's really important about molarity? There's something you have to know. What do you have to know about molarity? Our molarity of something is always going to be in moles per liter. That's the definition of the unit of molarity, moles per liter. So that's basically, by saying molarity, it's saying what is the concentration in moles per liter of my solution, right? Okay, so we have 4.20 moles of ZnCl2. In how much volume? 250 milliliters. So now all I have to do is convert my units to match the units of molarity. So moles is okay. What do I need to change? Milliliters. I know I have 1,000 milliliters in 1 liter. So what do I get? Put it into your calculator. 4.2 times 1,000 divided by 250. 16.8 moles per liter ZnCl2. What's another way that we could write this? You just write 16.8 and you say molar and you put a big M, ZnCl2. It's the same thing. I don't know why. I guess I must have put up the blank one instead of the one that I worked on the video. Oh well. All right, what is the chloride? Oh, no. Y'all, we should be doing just the evens, not the odds. Come on. Y'all keep me on track. All right, so same thing. What's the molarity of, we have a 750 milliliters containing 2.10 moles of Na2SO4. Okay, so I want molarity. So molarity is in moles per liter. So what am I going to do? Just convert my volume. Y'all put it in your calculators. I should hear some calculator clicking. You know, that's one of my favorite sounds. 2.8 moles per liter. And we could also say that as 2 molar Na2SO4. 2.8, sorry, molar. Good.
Will it just be molar on the exam, or?
You have to recognize either way. So on the exam, you have to be able to recognize either way. That's why I started. This is one you have to know. Okay? Have to know. All right. So only the evens, only the evens. What is the potassium ion molarity? Molarity is the same thing, moles per liter, of 850 milliliter blood plasma containing 10 millimoles of K+. Now what's the problem? We have 2 units we need to convert, right? So what do we want to convert first? Let's go millimolar. So we know we have 1,000 millimoles in 1 mole. We also know that we have 1,000 milliliters in 1 liter. So we cancel our millimoles. We cancel, ooh, I did not mean to cancel moles. Cancel our milliliters. We're left in moles per liter. And what you can recognize is that these two will cancel each other out. So you really could just take 10 divided by 850 and it would still give you the same answer. So what do you get? 0.012 moles per liter, or 0.012 molar. Okay. But this is dimensional analysis coming back in full force, huh? How many grams of NaCl must be added to water to create 2 liters of a 0.54 molar normal saline solution? This is something you might actually have to do. So how do you do this? This one's a little different than what we've been doing in the past. What are you starting with? I know I have a 1.54 molar, but what is molar? What do you mean that's on the other side? Of the what? On the left side of the equation. What do you mean? You could start anywhere in the dimensional analysis. Right, moles in 1 liter. And what are we trying to get to? Total number of grams. How do we convert to grams? The molar mass. You'll have to pull from way back when, right? The molar mass. So if I need to go and get the molar mass of sodium chloride, molar mass NaCl, what do? I need to go get my grams of sodium and my grams of chlorine, and then I multiply times the number of atoms of each. There's only one of each. So how many grams in sodium? 22.99 plus how many are in chlorine? 0.45. Okay, so that gives me what? 58.44. And what are my units on this? Grams per mole. Okay, so now I need to make sure that when I put this conversion factor in, I cancel out what I want to cancel out. I really want to cancel out moles, right? So I'm going to put moles on bottom. I'm going to get 58.44 grams of NaCl. So my moles cancel. I'm left in grams per liter. But is that the unit I want to be in? No, I need to get rid of the liter. I just want grams. So how do I get rid of the liter? I was told that this was 2 liters. My liters will cancel. 1.154 times 58.44 times 2. I get 18. Is that what you get? Okay. That one's a little bit tricky. That's probably going to be one of the hardest ones. All right, now we have to start calculating some of those percents. So if you're going to calculate a percent mass by volume, what are my units for a percent mass by volume? The mass is in units of what? Grams. My volume's in milliliters. And that's on your sheet, isn't it? Yeah, that's on the sheet. I mean, you don't have to remember that. You just have to use it. Okay, for each of the following solutions, let's do A. We have 75 grams. Let's write our formula before we do that. What's our formula? Our percent mass by volume is equal to grams of whatever the part is over milliliters of, so L-U-T-I-O-N, solution times 100. All right, so this is the formula we're going to plug into. So we're trying to calculate the percent by mass, so that's telling us this is our unknown. Okay, so we're going to say our percent mass by volume is equal to my grams of the part. Well, that's 75 grams of my solid, Na2SO4, in a total of water and my solid together being 250 milliliters. So what's my percent mass by volume? Oh, times 100. How much? 30? I didn't write this one down. Like I wrote my formula and I didn't. 30%? Is that what y'all get? Yeah? Okay. I don't know. I didn't write my answer down for that one. Charles must have come in and then asked me something. All right. So B, it's the same thing. We're trying to solve for percent mass by volume. So my part in this case is going to be my grams of sucrose. And then I have a total solution of 355 milliliters. So this is 35 grams sucrose over 355 milliliters. It's 35? Oh, 39. Sorry. 39. Thank you. What do we get? 11%. And usually if you're going to express this, like if you didn't have this part here, I would say 11% mass by volume sucrose. Like that's how you'll read it on a label, something like that. That's how you'll see it. No, because that's really mean. And here's the thing with that. So the question is, are you ever going to just get the solvent volume and not the solute volume? And the answer to that is no, because sometimes when you add two things together, it's additive. And sometimes when you add two things together, it's not perfectly additive. Like you can't say I had 5 grams of this, so that's going to bring my total volume that was 10 milliliters of water up to 15 milliliters. It doesn't work that way. So we're not going to expect you to do that. So that's why when we're making a solution, right, we say, okay, I'm weighing out my 5 grams of whatever it is, and I'm going to put it into my beaker or my graduated cylinder, right, something that can measure volume. And I'm going to pour water until I fill it up to a particular point. We're not going to put 250 milliliters and maybe you have 100 grams of stuff, right? And it's going to take up room, it's going to take up volume. And so it would change your final volume. So that's why we say we add our solid, then we add water up to whatever our solution volume is. That's a great question. Okay. So moving on. Okay, now we're going to do a mass by mass. What's our units for mass by mass? Grams over grams. It's really important to know your units. Okay, so we want our percent mass by mass. And so all we're going to say is grams of the part. So we're going to mix 10 grams of KCl with 100 grams of distilled water. Okay, well, just put the part 10 grams KCl over the solution, which is 100 grams of water times 100. What do you get? 10%, right? Because your hundreds actually cancel. So you end up with 10% mass by mass KCl. Okay. All right, now, this is something that you might have to do in the lab, right? How many grams of NaCl must be combined with water to prepare 500 milliliters of a 0.9% mass by volume physiological salt or saline solution, right? Physiological is what we see in our cells. Mass by volume is what unit? Grams per milliliter. Okay, so let's just use our formula, right? We have a 0.90% mass by volume equal to X number of grams of NaCl, this is our unknown, over, we're going to prepare 500 milliliters of our solution times 100. So what do? What do y'all do? Y'all what do you say? You cross multiply, or do you, I do the inverse of whatever's with my unknown. That's what I say, but I'm not trying to confuse y'all, right? So you multiply this by 500 and then divide by 100. Bless you. Right? Because whatever you do to one side, you got to do the other. If I'm trying to get rid of the 100, I want to divide by 100. If I'm trying to get rid of the 500, I multiply by 500. So what you do to one side, you do to the other side. It doesn't matter. Doesn't matter. Doesn't matter. Whatever floats your boat. All right, so what do you get in grams? This should equal our grams of NaCl. What do we get? 0.45? Oh, 4.5, I'm sorry. 4.5 grams NaCl. All right, now, you're probably not going to have a whole lot of experience with parts per million, parts per billion, right? But you only use these if you only have a tiny, tiny, tiny amount of stuff in solution. If you're given something that's a percentage and it's 5%, right? That's kind of a lot compared to something that's a parts per million or a parts per billion. So I really want you to just understand that we use this for solutions that have a tiny amount of solute inside of them, okay? It's mostly solvent. All right, so what's the concentration in parts per million of a solution that contains 150 milligrams of copper and 100 milliliters of tap water? Is there a formula for this? Is it on your sheet? Oh, it is. That's so nice. What is it? Over milliliters of solution times a million. I had to think about that. No, my son asked me the other day, it's funny the things that you know and the things that you don't know, because he says, how fast can a human run? And I'm like, oh, dude, I don't know the answer to that. I mean, you know, I don't know. 30 miles per hour, 25 miles per hour, I don't know, something like that. He goes, well, how fast can you walk? I'm like, God, I don't know. And then he goes, well, how fast is the speed of light? I said, oh, 3 times 10 to the, he's like, Mom, you're so weird. Like, oh, you had one that I knew. All right, so what do you get in parts per million? So our grams of solute are, what do we have to do? We can't plug this in right away, right? We have to say 1.50 milligrams. We say there's 1,000 milligrams in 1 gram. So how many grams do we have? 0.0015? Yeah. So now that's what we plug in. Our parts per million is equal to 0.0015 grams over, we're still in milliliters, so that's great, times a million. Right, percent was times 100. Now we're multiplying times a million. So what do we get? 15 parts per million. So use those formulas, y'all. Use those formulas. Okay. All right. How many liters? Now we're doing dilutions. Oh, dilutions, y'all. If you just remember the one formula, dilutions are not bad. You just have to remember that one formula. What's your one formula? CI, VI, CF, VF. Some of y'all might have learned M1, V1 equal to M2, V2. Anybody learn that one? It's the same thing. It's exactly the same thing. What's M stand for? What's the big M? Molarity. So it's a concentration. But we typically use a C because it doesn't have to be in molarity. It can be any concentration unit. So if you learned M1V1 equal to M2V2, it's the same thing. You can use that. Okay, so how many liters of a half normal saline IV solution with a concentration of 0.45% mass by volume can be prepared from a 1 liter of a 9.0 mass by volume stock solution? The only thing that you're trying to figure out is what's initial and what's final. Initial means stock. What are you starting with? You're starting with a stock. A stock is a high concentration. Right? It's really hard for labs to store huge volumes of really, really low concentration stuff. So typically what you're going to see is that if you need to make an IV solution, you need to make whatever it is, you're going to have a stock that's at a high concentration and you'll have to dilute it in order to get the working concentration that you want to give to a patient. Okay, it just makes more sense storage wise, makes more sense in terms of containers that you have to put it in, all that kind of stuff. It's just easier. So our stock is right here. This is our stock solution. So that's going to be our initial. So our concentration is 9.0% mass by volume times my volume, which is 1 liter. Now, it doesn't actually matter what your concentration units are and what your volume units are, as long as they are exactly the same on the initial side as they are on the final side. Okay, so you don't have to usually do a whole lot of conversions here. So I want my final concentration to be 0.045%, not 0.045, just 0.45. Okay, and then I don't know what my volume final is. So I divide. And I like to put my units because I like to see that they really do cancel out. They really do cancel out. Okay, it's just a good step to take. So what's my final volume that I need? I need 20 liters of my final solution. Okay. All right, so a patient order requires 1 liter of a 0.5% benzoalkyl chloride antiseptic. You have a 12% stock solution. How much stock solution will you need to prepare the order? This is exactly what you're going to see, just like this, where you're told this is your stock concentration and this is your final volume. That's how you're typically going to see it. So you use that exact same formula. CI, VI, CF, VF, right? So my initial in this case is my stock. Here's my 12% stock solution. So I know that that is 12%. I don't know my initial volume, but I do know my final. I have a concentration of 0.5% and I have a volume of 1 liter. So how much of that stock do I need? Takers? 0.042 liters, right? But who measures that? Who measures that? Sometimes you have to stop and think. This is a correct answer. But how would you measure that? You convert it to milliliters, right? You convert it to milliliters. So in 1 liter, you have 1,000 milliliters. So you get 42 milliliters. Now that's something you can use a graduated cylinder and actually measure with. Okay. Well, if I ask you for milliliters, you have to give your final answer in milliliters. But what if I say, how much stock solution? Well, what if I give you some answer choices in liters, but those values aren't correct, but I give you a milliliter where it is correct? You have to be able to do that. Yeah, it's a good question. It's a good question. All right. How would you prepare 2 liters? Now be careful with this. This is how would you prepare. This is not just what volume. This is, you're going to actually have to explain something to me. How would you prepare 2 liters of a 1 molar MgCl2 from 5 molar MgCl2 stock? Okay, so I know my stock, CIVI, CFC, yeah, FVF. Okay, so my stock is 5 molar. I don't know what volume. And I have 2 liters. I want to make 2 liters of a 1 molar solution. So what's my volume? I got 0.4 liters. Okay, now, what should I say? You need to add 0, and we're not really going to say 0.4 liters because, like, if it's less than a liter, typically you put it in milliliters. So how many milliliters is that? Add 400 milliliters of my stock 5 molar MgCl2, right, to enough, move this, to enough water to fill to how much? 2 liters. So all that's saying is that you put your concentrated stock solution in the beaker first. Then you add water to it so you don't overfill it. Does that make sense? Yeah. So always put your more concentrated and then add your water to dilute it so that you don't over dilute it. And then you give your patient the wrong concentration of ions and then, right, that's not good. Okay, you must prepare a 400 milliliters of a disinfectant that requires a 1 to 8 dilution of a stock solution. How much of the stock solution will be required? There's a formula for this on your formula sheet. Go look at it right now. Go try to find it. Give you a second. Then I'm going to show you a different way to do it too. What do you find it? Should be VI is equal to VF divided by our dilution factor. Did you find that? It should be there by all your concentration formulas.
In the book it says dilution factor equals VI over VF.
Dilution factor is equal to what?
VF over VI.
VF over VI. Okay, I just rearranged it. That's all it is. I just rearranged it. So I cross multiplied these two. So you can start with the original, what you see in your book. We can do that so that it's what you see in your book. Okay, so you must prepare 400 milliliters, right? How much of the stock solution will be required? Well, I want to know, this is my unknown. So for me, it's easier to rearrange the equation before I put the numbers in. Doesn't matter to me how you want to do it, but you're solving for the initial. So, right, times VI, and then divided by your dilution factor. VI's cancel, dilution factors cancel. You end up with that. Right? Y'all okay on that? No? Yes? No. Okay. So if you have it was dilution factor is equal to volume final over volume initial. Let's plug it in, and it might be easier for y'all to see plugged in, right? So what is your dilution factor? It's a 1 to 8, so it's a dilution factor of 8. What's your final volume? We're trying to prepare 400 milliliters. And what was my initial volume? This is my unknown, right? So you can just cross multiply and get VI is equal to 400 milliliters over 8. Better? Okay. More than one way to skin a cat. So what do you get? 50 milliliters of my stock. Now I'm going to show you an easier way. Do you want to see an easier way? Yeah. Okay. CI VI equal to CF VF, right? When you have something that has a dilution factor, if I say I'm going to dilute it 1 to 8, that means that you're going to dilute it by a factor of 8. So if my stock is 8x, my working solution is going to be 1x, right? That's what a dilution factor means. So if I say that my initial concentration is my highly concentrated, it's 8x, right? I need to know how much volume I need to get a final concentration of 1x times 400 milliliters. Guess what you get? Divide by 8, you get the same thing, 50 milliliters. You don't need to remember a new formula. You just need to know that when you talk about those dilutions and those dilution factors, all you're doing is saying that your final solution is going to be a 1x and your stock is going to be whatever they tell you the dilution factor is. So either way, we give you exactly the same answer. Okay. Whew. Osmosis and diffusion. This is our last section? No, but the last section is really, really short. Really short. Okay. So y'all remember my little drawing that I did for y'all? I love my artistic ability. Okay. So if you're trying to remember things that are hypo and hypertonic, how do you remember? Right? This is how I remember a pot. I'm going to pour water into a pot, right? Here's my pot with a handle. I'm going to pour water into my pot, right? So if you have a hypotonic solution and I have a cell in the middle here, what direction is my water going to go? Into the cell or out of the cell? It's going to go into, water goes into the cell because you pour water into a pot, right? I'll give you the scientific stuff in a minute, but it just helps to know. Okay, so per, right? What do I think of when I think of per? This is my cat, right? It's a sad looking cat, but I always give him a fat body and a tail. He looks terrible. But what does a cat do? A cat purrs, and when the cat purrs, that sound comes out of the cat, right? So water is going to do what? Come out of the cell and enter the solution. Okay, that's my little craziness for this one. But what is this? Why, right? If you have a hypotonic solution, that means that you don't have a whole lot of solute particles in the solution. You have more inside the cell. So water is going to travel to dilute those solute particles inside the cell, and so water is going to enter the cell, right? If you have a hypertonic Hyper means you have a lot, right? You know a kid that's hyper, like my 8-year-old? Hyper. It's crazy, right? Lots of energy. We have lots of solutes inside of the water, inside of the solution, right? So what's going to happen is the water is going to leave the cell and try and go dilute all of the solute that's inside the solution, okay? So either your cell is going to swell, in this case your cell would swell, and in this case your cell would shrink. So that's the cell. Why does it do that? Make sense? Okay, so we have a lettuce leaf. It's in the produce aisle at the grocery store, and it's accidentally submerged in water. Will water exit or enter the lettuce cells? What do you think is going to happen? It's water. It's just water. Do we have a lot of solute particles there? No. But inside of a cell, do you have solutes? Lots of them, right? So which direction is the water going to go? It's going to enter. It's going to go into the cell. Will the cells swell or crenate? Crenate is shrink. They will swell. Is tap water hypertonic or hypotonic to the lettuce leaf? If it goes in, like you pour water into the pot, what do we call that? Hypotonic. Now, do you see why that pot and the cat are important to remember? Otherwise, it gets really confusing. You need to practice this. I know that there are some extra practice ones at the end of the chapter. I would practice that. All right, we have a patient who is undergoing hemodialysis. That means their kidneys aren't working and we need to filter their blood for them. Because inside of their blood, right, they now have a lot of waste. So in blood, you have lots of waste. Right? That's why you're going to hemodialysis, to get the waste out. So as the blood leaves the patient, it has blank osmotic pressure than the dialyzing solution. What do you think? If the blood has a lot of waste particles, right, what's the water going to want to do? Go towards it and create pressure, right? So it's going to have higher osmotic pressure than the dialyzing solution. We go through this exchange process and we get rid of the waste particles. Now you have an equal number of solute particles in the blood as you do the dialyzing solution. So tell me, what is the osmotic pressure when the blood re-enters the patient? Because remember, osmotic pressure is all about how many solute particles you have and how the water will move and create pressure. It's going to be equal. It's got to be equal. It's got to be the same as the dialyzing solution, right? That's the whole point of dialysis. That's how dialysis works. That you have the patient's blood and then you have this dialyzing solution. And because you don't have a whole lot of particles here, the waste particles will move into the dialyzing solution, but the blood will stay. So by the time we're done with dialysis, you have equal amounts of solute in the dialyzing solution as the patient's blood. And that's how dialysis works. Okay. All right. Will a red blood cell undergo crenation, lysis, or no change in each of the following solutions? Ooh, this is a little bit of a tough one because we have to remember two things. What are my physiological concentrations of substances inside of the blood? There are two. One of them is NaCl and one of them is glucose. Zero point 0.09% NaCl, 90, not 9. Sorry, y'all, 90. Sorry. No, that's just me swapping numbers. Okay, and then how about glucose? 5%. Now the glucose is mass by volume, right? What is the NaCl? Same thing, mass by volume, okay? So just kind of keep that in mind. All right, so we're gonna put our cell, why did I do that? Look at that. I got ABCD twice. I don't even know how I did that. All right, if we have 10% mass by volume NaCl, what that means is we have a cell that is at 0.9% here and 10% here of NaCl. Which way is water going to go? Water goes to higher concentration. Water is going to go out of the cell. What's going to happen to the cell? It's going to shrink or it's going to crenate. Shrink. Okay, so let's try another one. Always draw. If you get a little lost, draw your stuff out. It's okay. Not a big deal. All right, distilled water. I still have 0.9% in the cell. Distilled water. What is distilled water? It's no ions, right? The distillation process, you boil away everything that's not water, basically. So you basically have 0% here. This is why you shouldn't drink deionized distilled water. You know, you need the ions. So what's going to happen? So now water is going to enter, right? It always goes to areas of higher concentration. This is my water. So what's going to happen to the cell? It's going to swell, that's W-E-L-L, and then lyse. L-I-S-E, lyse, L-Y-I-S. That's lysis, but anyway, not a spelling class. Okay, next one. We have 5% weight by volume NaCl. What's going to happen? We're still going to areas of higher concentration. So my water is going to go out of the cell, and what's going to happen? Shrink, crenate. Okay. Now what? Now we have glucose. So change your cell, and inside my cell I have 5% glucose. Oh no, I do not. Yes, I do. 5% glucose. What's in my solution? 5% glucose. So what's going to happen? Nothing. You're going to have no change. It is isotonic. So no change. It is isotonic. Okay. So all you have to do for that is remember your two figures, right? Okay. We have one question left. One question. All right. Before we answer this question, I want to look at each of these three things. Identify the type of transport, passive, facilitated, or active, that will occur for the following molecules. Before we look at individual molecules, can we say what are some things that undergo passive diffusion? I need small, right? Small things. How about polar or nonpolar? Nonpolar. And there's one other thing that is polar that can diffuse. There's one thing that's polar that can diffuse. And we just talked about it. Moving across the cell membrane. Or water. Water can either go through facilitated transport, like a pore, or it can just simply diffuse, either one. So water is kind of funky that it can do more than one thing. Okay, so facilitated transport could be water. We'll put that one in both categories. What else? Ions. polar molecules. How about active transport? Active transport can be anything. So how do you tell the difference between facilitated transport and active transport? So for active transport, energy is required. And then for facilitated transport, you need no energy input. This is like, do you go through a tunnel or do you go through a toll booth, right? If you're going through a toll, you have to pay them money before they'll let you through, right? So a lot of times what happens in active transport is that we are transporting against the concentration gradient, right? Against the concentration gradient. So that means you're trying to transport something that's at a low concentration to an area with a high concentration. And things don't naturally do that, right? Whether it's passive or facilitated diffusion, you have to be moving from an area of high concentration to low concentration. Have to. Let's write that. Both of these, you're going from area of high concentration to area of low concentration. And brackets just mean concentration. Of solute. Well, it doesn't really matter. Honestly, it's the same thing. Honestly, it's the same thing. It depends on whichever substance you're talking about. If you're talking about transporting salt, right, then the salt's going to move from high concentration to low concentration. If you're talking about water, water is going to move from areas of high water concentration to areas of low water concentration. It just depends on the substance you're talking about. Yeah. Okay, cholesterol, no energy is required. Is cholesterol polar or nonpolar? Well, it's generally nonpolar. It's got a hydroxyl group on it, usually at least one, but it's not very small, right? You remember when we drew that that nucleus, the cholesterol nucleus, and it was a bunch of rings, and then we had to add a bunch of chains of carbons on it. You remember that? Was that small? Yeah, not really. No. So it's mostly nonpolar and it's relatively large. So what should we use? Facilitated transport. Okay. Nitrogen. Nitrogen exists in nature like this. So we call this N2. Polar or nonpolar? A nitrogen bound to a nitrogen, they both have the same electronegativity. So is it a polar bond? No. So can it be a polar molecule? No. So it must be nonpolar. So if it's nonpolar, and look, it's only 2 atoms. It's only 2 atoms. That's tiny. So what kind of transport? Passive. Okay. Cl minus, no energy required. Polar or nonpolar? Polar, it's charged. So passive or facilitated? Facilitated. It can't be active because there's no energy. So this is facilitated. Okay. And then H plus, energy required. Energy required, active. Okay. All right, that is it. Don't forget that your homework is due tomorrow at 9 p.m. Please, 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 please get that homework in on time. Good luck. Everybody stay safe with the tropical storm. Let me know if you need anything. Okay, anybody have any questions on chat? nobody's got a question on chat, I'm going to go ahead and end the Zoom, and that way we can stop recording. But if you have a question, you can send me an email.